Okay, let's start a new topic. We're going to talk about rotational motion, and we're going to find that there are a lot of similarities between rotational kinematics and rotational dynamics, and linear kinematics and linear dynamics, what we call linear mechanics. When we start a new topic, we typically have some easy problems that are less challenging than what you might expect on an exam, and that's certainly the case here. We have problems 1, 2, and 3 in Chapter 9, going back a chapter, back to Chapter 9. Let's look at problem number 1. Number 1 is looking at the minute hand on your analog watch, and just what's the angular velocity of that. Now, you understand that angular velocity is a vector, and the direction of that vector is given by a very strange rule. We call it right-hand rule, and that is, as we discussed in class, there are only two directions that stay the same as something rotates about an axis, and that's along the axis, one way or the other. In this case, as this rotates, I either have this direction that doesn't change out of the page, or the direction into the page. So what we have to decide is which of those two directions are we going to assign to this vector omega. Well, by convention, this is not something physical or something the universe decided. This is by convention, a decision made by people long ago that probably were right-handed people. They decided that we would use our right hand, that we would curl our fingers in the direction that the object is rotating, and our thumb is going to be pointing in the direction along the axis of rotation that we assign to omega. So this omega vector is going to have a direction into the board by right-hand rule. Now, that's the direction. We need a magnitude for this vector. Well, that's just the angle that it goes through divided by the time that it takes. Well, the angle that it goes through, I know that this minute hand goes around once every hour, and once around is 2 pi radians for each 1 hour. Well, that's an answer. It's certainly correct. It's just not in the units that we normally associate with angular velocity. In MKS units, we typically use the second as the unit of time, and so what we would like is the number of radians each second. Now, to find that, I multiply this result by 1. Whenever you multiply something by 1, you don't change it. But there's lots of ways to write the number 1. I can write that 1 hour is 3,600 seconds. That's just 24 times 60. Now, I know an hour seems longer than that when you're in a physics class, but that's really all it is just 3,600 seconds. And so if I multiply this out, I get a number that is fairly small. I don't remember what it is, but 1.7 times 10 to the minus 3 radians per second. Okay, so that's problem 1. If this watch were on your wrist, like my Mickey here, then my answer would be into my wrist by right hand rule instead of into the board by right hand rule. Either way. Let's look at problem 2. It's more interesting, but not that much more difficult. In this case, we look at the Earth, and there's the North Pole. That's where Santa lives, okay? And we've got the axis of rotation. The Earth is rotating about this axis, actually that way. And they talk about an individual that lives on the equator and someone that lives in Bozeman. Bozeman's about at the 45th latitude, and so about halfway between the equator and the North Pole. And they're asking us to compare the angular velocity, the omega for Bozeman, versus the omega at the equator. Well, that's the whole point of even worrying about angular mechanics, is that we find that every part of the globe that's attached, that's moving together as a unit, we call that a rigid body, they're all rotating at the same angular velocity. They both go through the same angle in a second. And now, that doesn't mean they have the same linear speed. You know, linear speed is just how far down you get the road each second. And this person at the equator is going around a much bigger circle in the same time that this person in Bozeman is going around a smaller circle. But they both go once around, that's 2 pi radians, in one day, 24 hours. And so the omega for both is going to be 2 pi radians divided by 24 hours. Now, again, the units of omega are, that we want to use, are radians per second. And so we would again multiply this by 1, and I can write 1 as 1 hour is equal to 3,600 seconds. And that's going to give me an angular velocity of 7.3 times 10 to the minus 5 radians per second. Now, the direction, you're going to have to be a little bit creative in describing the direction. You know that if I had a globe up here, an actual physical globe, that globe would be rotating such that Los Angeles was heading towards Boston. That's the way the world turns. Boston gets morning before we get morning in Bozeman, and we get morning before Seattle gets morning, just because we're rotating this way. And so if I use the right-hand rule, that means the omega vector, by definition, by convention, is going to point up through the axis of rotation. And if Santa's workshop is right on that axis of rotation, then I could say that it points right up through Santa's workshop. The other way I could answer this is that the the axis of rotation points towards what we call the North Star. And so we could say that the omega vector for the Earth's rotation points towards the North Star. Or, if you don't like any of those suggestions, just draw a picture, okay? Picture's worth 1,000 words, so Greg, shut up. So there we have it. Now, the third problem, a little out of place with the lecture, but not out of place with the reading that you're supposed to have done so far. The third problem involves using the rotational kinematics equations. Let me just quickly review those. The linear kinematic equations were driven by the fact that velocity was defined as the change in position with time, and acceleration was defined as a change in velocity with respect to time. Well, with rotational motion, we have angular velocity, and that's going to be the change in angle with respect to time. And I've left the vector signs off of these, just talking about magnitudes here. And we have an angular acceleration, which is the change in angular velocity with respect to time. Now, if I had a constant acceleration, we found that this led to 4 kinematic equations, that v final was equal to v initial plus the linear acceleration times the time. We found that the displacement was the average velocity, which is 1/2 the initial plus the final times the time. We found that we could put these two equations together in such a way to eliminate v final, and we get delta x is equal to v initial delta t plus 1/2 a delta t squared. And then we could combine these first two equations in such a way that we eliminate time. And in that case, we got v final squared is equal to v initial squared plus 2a delta x. And if things were going in the y direction, we just replaced all the x's with y's. Well, now, because of this similarity in relationships here, we have 4 equations for angular velocity that are just parallel to these equations for linear motion. And so instead of linear velocity, I would have angular velocity final, and that's going to be the initial plus the angular acceleration times the time. We're going to have a change in angle that's going to be 1/2 the initial plus the final, delta t. This is just the average angular velocity times the time. And then I'm going to have another equation where I combine the first two to eliminate omega final. And that's going to be omega initial delta t plus 1/2 alpha delta t squared. And then I combine the first two in such a way to eliminate time, and I get omega final squared is equal to omega initial squared plus 2 alpha delta theta. Okay. Now, you remember how we used these equations to solve linear problems. We always set up our 5 players for any kinematics problem, and that was delta x, a, v initial, v final, and delta t. And we had to find 3 of those in order to proceed with the solution to the problem. Well, now, instead of linear variables, we're going to have the corresponding angular variables. Instead of how far down the road, it's going to be how far around the wheel. Instead of linear acceleration, it's going to be angular acceleration. Instead of linear velocity, it's going to be angular velocity, initial and final. And time is just time, whether you're going around in a circle or down the street. So in this problem, we're told that there's a wheel, and this wheel is turning that way. Now that's going to give me an omega out of the board. We're also told that it starts from rest and that in a certain amount of time it makes 30 revolutions. So its angular displacement is going to be 30 revolutions. And that during that time it has an angular acceleration of 3.77 radians per second every second. And it starts from rest. Now, in part A, we're going to look for the time, and in part B of this problem, we're going to look for the final angular speed. Okay, so I'm going to get rid of our linear equations. We're not going to need those in this problem. So for A, if I'm looking for time, and I know these three pieces of information, and I want to know time, that makes the final angular velocity the who cares. And that means I should go and use the equation that doesn't have omega final in it. I don't know omega final, and I don't want to know omega final, so I should not have an omega final in my equation. Well, there's an omega final, there's an omega final, there's an omega final. It's this equation, that third equation, that doesn't have omega final in it. So I'm going to use it. Now we've got a little bit of a problem with units here, and that is that we've been given a non-standard unit for our angular displacement. 30 revolutions means that it went around in a circle 30 times. Well, what I want are radians, as we discussed in class. And so if every time around, if every revolution is 2 pi radians, and I've got 30 of those, this is going to be the same as 60 pi radians. Okay? That's just 30 times 2 pi radians. Okay? 60 pi radians. So now I can plug into this equation. I've got 60 pi radians is equal to, this goes out because we start from rest, and we have 1/2 times 3.77 radians per second times delta t squared. Well, that is going to give me a delta t squared is equal to, multiply both sides by 2, 120 pi radians divided by 3.77 radians per second squared. And if I take the square root of both sides, what I get is delta t is equal to, oh, look at there, 10 seconds. Looks like the numbers were cooked, don't you think? Looks like we chose that number just right so that it would turn out to be a nice clean number that we could easily write down. Well, now if we know that this is 10 seconds And now we want to know for part B what the final omega is. Now we have 1, 2, 3, 4 pieces of information, and that means there's going to be 3 different equations that I could use here that would each give me the same right answer. I can use this equation to get omega final, I could use this equation to get omega final, or I could use this equation, this equation to get omega final, not this one, okay? So, whenever I have a choice, I choose one of the first 2 because they're the fundamental equations. So part B, I'm going to choose that first equation, omega final is equal to omega initial plus alpha delta t. Well, that's 0, so this is going to give me 3.77 radians per second times 10 seconds. I can do that in my head. That's 37.7 radians per second. That's the magnitude. Now, because this thing is rotating counterclockwise, the omega is going to be out of the board by right-hand rule. And because it's speeding up, you can't slow down from rest. If it's speeding up, I know that my alpha vector is in the same direction as my omega vector, okay? And we discussed that in class. Okay, that's been homework set number 30. I hope that you found it fairly straightforward. Thanks for watching.